So exponential functions is lecture 19. So in this lecture, hopefully you when you learn this, you could be able to identify an exponential function when you look at the formula. Also, you could be able to recognize the graph of an exponential functions, and we use the graph of exponential functions to do all the transformations. Okay, so the transformations that we cover in this course include vertical shift, horizontal shift, reflections with respect to the x-axis, reflection with respect to the y-axis. Okay. So first, I'm going to give you the definitions of exponential function, and we look into the graphs of the function. So for today's lecture, mostly we look at the formula of exponential functions, manipulate the graph of exponential function, and later on this week, we're going to look at logarithmic functions, and then we're going to solve exponential and logarithmic equations where you can see the connection between exponential functions and logarithmic functions. Okay, so definitions of function. F represented by f of x equal to capital C times a to the power x, given that a is different from 1, a is greater than 0, and c is greater than 0, is called a exponential function. Yes.
The last one, that's greater than 0, what is that?
C, capital C. So which is the constant in front of it? So this is the formula, general formula for an exponential function. Okay. And from there, we can do a lot of manipulations on the value of C and the value of A so that we can get different types of exponential function. But overall, the domain of the exponential function is always all real numbers, or from negative infinity to positive infinity. Always for any exponential function, you got that all real numbers domain. Now depends on the value of A. So A is very important that you have a different type of exponential functions. When A is greater than 1, you have something called the exponential growth. And when A is between 0 and 1, you have something called exponential decay. So when A is greater than 1, you have exponential growth. And when A is between 0 and 1, you have exponential decay. So the information that I give in the definition is very important. As you can see, A has to be different from 1. I will talk about that in a little bit. And A has to be greater than 0. Because when A is greater than 0, you can actually define this to be right here for two different types of exponential functions. All right, so exponential growth is most likely affect you when you think about population growth. Even though it's not realistic model, but is a model to consider. I always try to bring back the COVID model at the start of the pandemic. The number of infected cases when you read the newspaper increase exponentially. This is the model that I apply, exponential growth. So something like this is called exponential decay. Eventually, when you have population or something, will die, eventually die down. But we'll never actually get to 0. So this is, we will learn a little bit later that y equal to 0 is a horizontal axis. So the function approach y equal to 0, but never actually will pass 1 to 0. So the first graph is for exponential growth. A is greater than 1. And for the second graph, you have exponential decay. Now let me go back to the conditions one more time. So I want to specify that A is different from 1. If A is equal to 1, then 1 raised to the power x is going to be 1. Then the function becomes a constant function. It's no longer an exponential function. Right? So therefore, we have to include this condition that A is different from 1. Because if A is equal to 1, you have that f of x equal to c times 1 to the power x, or equal to c, which is a constant function. And not an exponential function. So that's why we avoid a equal to 1. So a lot of students in pre-calculus and even calculus 1 get confused between the two types of functions, exponential functions and power functions. So you have to be careful when you look at the functions, okay? So the exponential functions, the variable is on the exponent, okay? The power functions, the power is just a constant. You see the difference? All right, so let's write it down. So there is a big difference between y equal to a raised to the x. So this is an exponential function. In this case, I just say capital C is equal to 1 for easy consideration. Okay. So here, a raised to the power x, this is an exponential function because x is on the exponent. And y equal to x raised to the power a. So this, the second function, is the power function. So let me know it here. Exponential function. And this one is a power function. Okay, now the difference between these two functions are, so the first one, exponential function, the base is a constant. So the base is a constant. This exponent is a variable. So let me write that down first. So the base is a constant, and the exponent is a variable. And for the power function, the base is a variable. And the exponent is a constant. So this is even here is just a note, it's just a bullet point, but this is very important for information for you to know, so that you can distinguish between exponential function and power function, because when you get to calculus, there's something called differentiation rules, and you need to be able to distinguish exponential function and power function to apply it correctly. All right, now let's move on to another topic. It's called properties of exponential functions. So you see a couple of properties earlier in the definitions, but here we get to more details. How to find the domain, the range, vertical asymptote, horizontal asymptote, and other stuff. All right, so the domain of any exponential function is all real numbers, right? Or from negative infinity to positive infinity. And we are considering exponential growth functions, right? Because A is greater than 1. So let me note it here. This is exponential growth functions. And this property is corresponding to the first graph. So A is greater than 1, exponential growth. So you get the domain of the exponential function already. What about the range of this exponential function? What is that? 2. So what is the range? 0 to infinity. So it's not going to be including the 0 on the left hand side or the left endpoints. Now the third bullet, you'll observe the graph of the exponential function here. So this is an increasing function. Right? When we read the graph, we read from left to right. So this is an increasing function, and this is a one-to-one function. So f of x equal to a raised to the x is an increasing function. And 1-to-1. Now, vertical asymptotes, there's no vertical asymptote at all for exponential functions. In this case, you have one horizontal asymptote, which is y equal to 0. Okay. Now, it depends on the functions that later on you will see that we manipulate or do transformation on exponential function, we have a different value for horizontal asymptote. But in this case, in this particular context, y equal to 0 is a horizontal asymptote. So for x-intercept, y equal to 0. Again, in this context, there's no x-intercept. However, it depends on the type of exponential function. We will see one x-intercept. So no x-intercept. In this case, y-intercept is 1, 0. Sorry, 0, 1. And also depends on the exponential functions that we are considering. . The last bullet, I'm gonna mention something that may not appear very relevant to us, but is extremely relevant to what we're going to learn in Calculus 1, that the graph is smooth and continuous with no corners or gaps. So these are the properties of an exponential function that you might want to consider. Okay. So I'm gonna put in a little bit more details here about when it's always going to happen with exponential functions. For example, it's going to be exponential function is always going to take from the positive infinity. The range depends on the function. You may have a different range. Okay. The function. So in this case, an exponential growth function. So this is always an increasing function in one to one. Vertical asymptote, always there's no vertical asymptote. Horizontal asymptote depends on the function. We will have different horizontal asymptote. X-intercept again depends on the function. Also, y-intercept depends on the function. And this is always going to be the case that the exponential function is always continuous and smooth. So always one depends. So this one is always, this one always. So this one depend. Depend, and this is always. Okay, so now let's move on to the second type of exponential function. This is exponential decay functions. So this is exponential decay functions. This is the case where a is greater than 0 but less than 1. And the domain is going to be the same. That's going from negative infinity to positive infinity. The range depends on the function, but in this case, the range is from 0 to positive infinity, but do not include 0. When we observe the graph of exponential decay function, you see that this is a decreasing function, but is still a one-to-one function. So f of x equal to a to the x for a between 0 and 1 is a decreasing function. And one-to-one. There's no vertical asymptote. There is a horizontal asymptote, which is y equal to 0. In this case, there's no x-intercept, but again, depends on the exponential functions of considerations. You may have one x-intercept. But in this case, there's no x-intercept. There's one y-intercept, which is 0, 1. And again, this exponential function graph is continuous and smooth with no corners or gaps. So the graph is smooth and continuous with no corners or gaps. All right, so I want to write down the detail like this about the range, the domain, horizontal, vertical asymptote, horizontal asymptote, x-intercept, y-intercept. Because when we get to the next lecture, which is logarithmic functions, remember I keep telling you that exponential function and logarithmic functions are inverses of one another. So therefore, when you consider logarithmic function, you just basically swap the range in the domain and the answer. Swap horizontal asymptote and vertical asymptote. Again, the answer of that is when you consider logarithmic functions, there's no horizontal asymptote for logarithmic functions, and vertical asymptote is x equals to 0. Got it? All right. X-intercept, y-intercept. Swap. Very simple. Yes. Now we're gonna move on to the next topic, which is the end behaviors of the exponential functions. So far, we just consider two types of exponential functions, exponential growth and exponential decay, which is more realistic in applied mathematics. So in the case of exponential growth, it's growth to if you consider x go to positive infinity, the population will go to infinity, positive infinity, which is unrealistic. And you let the world run forever, the populations will grow to infinity, which is unrealistic. They say at this point we will top at 9 billion, 10 billion, and the population will decay. When x go to negative infinity, that means you go back to the past, then the population will go down, eventually starting at 0, but it's not going to be 0, right? But so that's why I just use the arrow and not the equal sign, because population will approach 0, but not. For exponential decay, so you got start with something start with a population with a lot of people, a lot of members in the populations. So let's start with y approaches positive infinity when you go back in the past. And when you go to the future, the population will decrease to 0 approaching. So this second case, one of the examples that we can consider is the messenger pigeons that you can give the message to the pigeons and can fly and give the message to another persons. So at the beginning of the 20th century, the population died out because of all the hunting that occurred. So the population's starting a lot in the 19th century, but at the beginning of the 20th century, everything got down and eventually this distinct. Okay, so that's the example. Now I want to give you some multiple choice questions to work with. And most of the questions related to the type of exponential function that you have learned so far. So for example, the first multiple choice question, which equation below will produce a decay curve? That means which one is the exponential decay function. So think about that a little bit and let me know what that is. Let's do one first, and then I will show you how to do two and three and so on and so forth. All right, let me ask you this. How would you classify an exponential function to be an exponential decay function? What factor or what number should you consider to say that the function is decay function? There you go. So you look at the value of a, if a is between 0 and 1, then you say that that is an exponential decay function. So which one has that property? Is that A, B, C, D, C or D? D. So D is the options, right? Because A is equal to 1/3. For C, the constant is 1/2. So it doesn't affect the exponential function. Okay. So here the value of A is 3, so this is exponential. This is exponential. So D is the answer. Now, any questions on number 1? For number 2, they ask you which of the choices is an asymptote of the equation y equal to 2 times 3 to the x minus 1. So now remember, there is no vertical asymptote for exponential function. So automatically you can ignore C and D. You with me on that? Okay. Because there's no vertical asymptote. So you now that means you need to consider horizontal asymptote. Okay. So the horizontal asymptote, remember when we give definitions for horizontal asymptote, we tell you the end behavior of functions. Okay, so similar here, we go back to the definitions of the end behavior of the exponential functions. Okay. So again, in this case, is this exponential growth or exponential decay function? And how would you classify it? What factor should we use to classify that? Again, don't think about this function yet. Tell me, in general, how would you identify if a function is exponential growth? Like a greater than one, right? So a is greater than one, the growth. And then how to define a decay function when a is between 0 and 1, correct? All right, so this is the two cases that we need to consider. So for this function, what is a equal to? 3, right? A is equal to 3. So this is an exponential growth function. You okay with it? All right. So the -1 is there to do the vertical shift. Basically, this one shifted down by 1 unit. All right. So now let's take a look at you. We all agree this is an exponential growth function. So let's take a look at the end behavior. So you have here y approaches 0. So this is a horizontal. All right. So at x approaches -infinity, y approaches 0. But remember, you shift it down by 1 unit. You with me? So therefore, y approaches -1. Cool. All right. So again, without the -1 here, the end behavior tells you that the function will approach 0. But now we shift it down by 1 unit, that function will approach 4. So the answer is 3. Now, with that idea, can we try to do number 3? Okay, so first, identify if these functions are exponential growth or exponential decay. All right. So if this exponential growth or exponential decay, growth, what about that? Growth as well. About this, growth and growth as well. So they all growth functions. Okay. That means the function will approach 0. X goes to -infinity. And then you shift it up by 2 units. So this horizontal asymptote is y equal to 2, y equal to 2, y equal to 3, then y equal to 2. So to answer this question, which function below has a different asymptote than the rest of the other functions? The answer is C. Okay, so let me write a little bit of details, explanations here. So all of this, all functions are exponential growth functions. Right. But now they have different horizontal asymptotes. A, you have y equal to 2 is a horizontal asymptote. B, y equal to 2 as well. But C, you have y equal to 3 as a horizontal asymptote. And D, the horizontal asymptote is y equal to 2. So therefore, the difference is y equal to is C, which is y equal to 3. All right. Any questions? So in mathematics, in physics, or in any applied sciences, there is a very important number, which is an E number. Number E for that matter. So E in this case that we see is called the natural exponential number. And E is approximately equal to 2.71. So E is approximately equal to 2.71. And because this number is greater than 1, so this is called an exponential growth function. You will more likely to see an exponential growth function written in this form, e to the power x. The -6 is there for you to see that we do transformations by shift the function e to the x down by 16. So therefore, the horizontal asymptote of this function is x equal to -6. So here, exponential growth, horizontal asymptote is y equal to -6. Now to find the y-intercept, what you do is, again, y-intercept x equal to 0. Right? So when x equal to 0, e to the 0 is equal to 1. 1 minus 6 is -5. So B is the answer. So y-intercept x equal to 0. Right? You have y equal to e to the 0 minus 6, or 1 minus 6 equal to -5. So B is the answer. So this two example give you some idea of how to do transformation algebraically. Now we're going to do transformations graphically. But the first graph right here tells you to do vertical shift. The second graph tells you to do horizontal shift. All right, so vertical shift, you shift it up by, so this is the original function of x equal to e to the x. You shift it up by 2 units, all right? And here you shift it down by 1, 2, 3 units. Cool. Right? All right, so let's do vertical shift up. This is y, let me use another color here. Y equal to e to the x plus 2. Now you shift it down by 3 units. Do you see 3 units down? All right. You start here. Go 1, 2, 3. Yes, no, maybe. So here y equal to e to the x minus 3. Huh? Should be plus 2. Here, start at the original function. 1, 1, 2. Sorry, my bad. 3. Did I say 2? I mean 3. Sorry. My bad. So this is plus 3. Okay. Any questions? Thank you. Any questions? All right. So now we do horizontal shifts. So the original function is still y equal to e to the x, but for horizontal shift, we have to be careful with the representation of the function. Okay, you shift it to the right by 3 units. Okay. So this is y equal to e to the x. Because you shift it horizontally, the x value get changed, right? So x minus 3. So the minus 3 is in line with the x value, is in the exponent. Then you shift it to the left by 3 units. So you have y equal to e to the x plus 3. Again, in this case, the plus 3 is in line with the x value. You good with vertical shift and horizontal shift? Okay. Now, number 2, reflections with respect to the y-axis. All right. So reflection with respect to the y-axis, the x value got changed, right? So positive x changed to negative x, and negative x changed to positive x. All right, because it's affects the x value. So you write y equal to e to the negative x. Now, this graph is the reflection with respect to the x-axis. So the y value got changed. Positive y become negative y, and negative y become positive y. So the y value got changed, therefore, y equal to negative e to the x. Now, number 3. The graph of the functions. Now we do algebraic approach again. The graph of the function y equal to e to the x is shifted 6 units to the right. Okay. So shift it to the right, so x get changed. So to the right, 6. So x minus 6. Here is the options. Okay. And then 4 units upward, so plus 4. So D is the answer. So number 4, given f of x equal to 9 to the x, which of the following functions represents of reflections of the function on the x-axis and vertical shift of 5 units down. So reflections over the x-axis, y get changed, right? So positive y become negative y become positive y. So negative 9 to the x, right? So negative 9 to the x, right? So one option here, another options here, another options here. Okay, so we have 3 options in this case. Now, and a vertical shift of 5 units down. So vertical shift down. This is vertical shift down by 5 units. This is vertical shift up by 5 units. Okay, this is horizontal shift. So the answer in this case, C. The last question, you have seen this in the example in the last page already. What is the answer here? What is the asymptote? Again, there's no vertical asymptote, so therefore we can ignore C. Is this exponential growth or decay? Growth, right? So first you ignore this choice. No vertical asymptote. This is exponential growth. So what is the horizontal asymptote in this case? 3. Y equal to 3.